Hello viewers, so we have this question that says prove that the following equation is dimensionally consistent. Kinetic energy is equal to half mv². Now, for a formula to be dimensionally consistent, the left-hand side dimensions must be equal to the right-hand side dimensions. So let's check if this formula that we have here is dimensionally consistent. Let's start with the left-hand side. So we'll say left-hand side, we'll represent it by that. So on the left-hand side, we have kinetic energy. Kinetic energy is measured in joules. Energy is measured in the units of joules. It can be kinetic energy, potential energy, work energy. Any form of energy is measured in joules. So now, the unit of joules had the dimensions. We can get those dimensions from the formula of work. Let's say we have work is given by force multiplied by distance. So this is the formula for work. Now, from this formula, we can get the dimensions for force, get the dimensions for distance, and multiply those two. They will give us the dimensions for work. Those dimensions for work will still be the same dimensions for kinetic energy, which is in the units of joules. So those will be the dimensions for joules. So let's have that. Force, according to Newton's second law of motion, is given by mass multiplied by acceleration. This mass is measured in kgs, or the units of kgs, and acceleration is measured in meters per square second, like that. So that's what we have there in terms of force. All right. So this will be equal to kg. We can rewrite this in this format: kg m then s to minus 2. Now, in case you're wondering how we've come up with the s to minus 2 on top there, we're using the laws of indices. If you have 1 over x like this is the same as x to minus 1. If you have 1 over x squared, this is the same as x to minus 2. So this is the same rule we're applying even down there. That's why you're seeing that we have our s becoming s to minus 2 when it goes on top there. All right, so coming up with the dimensions for force, you find that the dimensions for force kg is mass, so it's represented by m. Then the meters is length, so it's represented by L, and seconds is time, so it's represented by capital T, and this is to minus 2. So these are the dimensions that we have for force. Yes. So let's get the dimensions for distance. Distance is measured in meters. Meters is a unit of length. So what we have as dimensions for distance is just the length. And this is what we have here. Now, bringing these two together, remember the dimensions for force must multiply by the dimensions for distance in order for us to get the dimensions for work, which is the same as the dimensions for kinetic energy, and those are joules. Yes. So we'll say our m, l, t to minus 2, these are going to multiply with l that we have there. And when we do our mathematics here, you find that we're going to get m, l. Now, l multiplied by l will give us l squared, and t to minus 2 on the other side is what we'll get. So now it implies to say these are now the dimensions we have for kinetic energy. So we can write it as kinetic energy is equal to m l to the power of 2, then t to minus 2, like that. Let me just rewrite that. This 2 here, yes. So this is to the power 2, and that is to the power of minus 2. So these are the dimensions that we have for kinetic energy. Yeah. So the left-hand side has got the dimensions of m, L to the power 2, T to minus 2. Now, the formula will be dimensionally correct or consistent if what we are going to find on the right side is the same as what we have on the left-hand side. So let's check that. Now, on the the right-hand side, we are given, say, we have mv². Half is a constant, so we don't consider constants in dimension analysis. So constants are numbers. Yeah, so numbers are not considered. Functions like trig functions, cos, sine, all those are not considered under dimension analysis. So if you see a number that's not considered, only physical quantities are considered here. So what we have is mv² on the right hand side. Now mv², m is mass, v is velocity. So what we have here is the mass is measured in kgs. This is multiplying by the velocity. Velocity is measured in meters per second. But remember, this must be squared because we have v² uh, in our formula there. Yes, so that must be squared. So when you square that, you find that what we'll get is this will be equal to kg, then it's multiplying by m² on top there, and down here we'll have s². So this is mv². It has got the units of kg, m² over s². Remember, this can be rewritten in this format again, where we are saying kg m². When we take the s² on top, it's going to be s to minus 2. The power becomes minus 2. All right, so it implies that these are the units that we have now for mv². And taking our dimensions there, you find that the dimensions we'll have is, so we'll have kg is mass, that's m. Then meters is length, so we'll have L², and s is time, so we'll have time, and this is given to the power of minus 2. So these are the dimensions we have on the right hand side. Now we can see that what we have on the right hand side is the same as what we have on the left hand side. We have m L² t to minus 2. On the other side, we also have m L² to t to minus 2. So it implies to say our formula is dimensionally correct. Yeah. So our conclusion is our formula, the left-hand side dimensions are equal to the right-hand side dimensions. Therefore, our formula is dimensionally consistent. You conclude by that statement. Thank you.